software walks you through the process and asks you to do certain things. Balance load is located here, so we're balancing the load, and as you can see, the load is now 0. So it means that machine is zeroed with respect to the load measurement. And well, next thing, I need to measure the gauge length, and so it is quite simple again to do. So I will just use my punch marks, and so here what I will do is I will just stretch my caliper to match the positions of the marks, punch marks, shiny. So I'm positioning my caliper this way, and what I see is that my distance is 2 inches. Click next. So record specimen name and original diameter here. So specimen name, let's put our 1040 steel annealed. So diameter, what the diameter we have is, take this with me here. It's 0.4975 inches, and here I have selected inches. So it's good to go to our next step. So our next step is loaded with some instructions, and we will need to read them carefully. We will have to position the sample first in the top jaw. So I'm going to move the upper jaw with this handle. A little bit upwards, and so I'm sliding it in, and my task here is to put it in between the jaw plates the way the sample will be hanging, but will be hanging freely. So I'm closing it just to make sure that there is not a lot of the gap between the sample and the jaws. And while I'm doing it, so I need to be careful which way I'm closing it. So really closing, not opening. So now it seems to be closed, and then quarter turn. Something like this probably, just to loosen the sample, because next step we'll need to fix the lower part of the specimen. Let's read next. So press down so the sample falls into the bottom rib, jaw or rib, yes. Make sure that no damage will occur. This second step, so simply by moving the sample to the right and moving the upper jaw or this rib downward. And let me show you what's going on here. So here my task is just to be able to slide the sample inside of the bottom jaw. So that's why I'm sort of ensuring the sample is sitting at the side, so it doesn't compromise the movement of the machine. So now I can move down. That sample can slide into the lower jaw easily. So now, let me put this back. And I will need to position it right in the center. So I'm sort of, you see, sliding the sample to the left. Push the sample to the side until it hits the stop and it's centered in the jaws. So I will just sort of maybe a little bit ahead. We'll close the bottom jaw, then loosen them 1/4 turn. So it is exactly what the second step was saying. And for this, I'm using this handle to close it. Right, so I'm closing. So the ribs are moving. Now I'm losing 1/4 turn on this. And now it's still moving, no problem. So next, rise the crosshead up using this button to remove slack on the sample, and continue rising until a load of between 0.3 and 0.5 kilopounds is applied. So I will need to look at this dial for measurement of force in order to not or to be able to locate the force between 0.3 and 0.5 while I'm moving upwards. So this is to pretension the sample, and let's go really slowly, accurately, to get just within the specified limits of this applied force. And looks like I'm really close, and 0.39 is perfectly fine, so I don't need to play with that more. We're going to our next step here. Tighten the top and bottom jaws, and always read these sentences until the end. So what it says is this should apply a load between 1.5 and 2.5 kilopounds. If not, call your supervisor. So if not, it means that your sample is fixed incorrectly, and upon application of the load, there might be some sliding of the sample with respect to the jaws, and or maybe sample geometry is not maybe as intended, sort of. So there's some problem because we usually need to see the increases in force. And let me double check. So it's between 1.5 and 2.5 kilopounds. And so I will start with the top one, or bottom, doesn't matter, but let's go with the one that is at the top. And as you can see, the force is going on. So now what I would like to do is tighten them equally. So there is an equal tension, or the jaws are closed equally. So the force will be transmitted during the test in the best possible way. So it looks like, you know, 1.5 is reached, so I can just tighten it a little more, so to be within these limits a little further. And now, next, attach the strain gauge. Squeeze the two buttons together to prevent damage, and position the strain gauge so it is touching only the sample. Click the balance strain 1 button. So balance strain. So we didn't do that, and we will do that in this step. So this is our strain gauge. Press these 2 buttons. Why? We would like to lock this and this spring, or more accurately, lock the levers that hold the springs on the place, so they don't move during installation of the strain gauge. And what I'm doing, I'm going really carefully, and as you can see, I can, you know, use the only one hand to slide them in. So what is needed is basically placing the round portion of the sample within this space over here, and at the lower part of the strain gauge. So I'm moving really slowly so you can guys see it. Okay, so I'm here. You see, sliding in. Be very careful with this exercise because it is very easy to break the strain gauge. It is fragile and very delicate piece of equipment. So now I'm releasing these buttons. And what I would like to point out as well is that my strain gauge doesn't touch, this box doesn't touch anything like grips and other parts that may interfere with the strain gauge. Why? Because any vibration, any input, like other than just sample, will skew the data. So we want it to be attached only to the sample. And I'm going to make sure that I don't have any strain on the springs. And so it's just to make sure that it is stretched across the specimen properly. So with this, we're moving to balancing the strain. So I'm balancing the strain now. It is zeroed, and we're ready to rock here. Now, how to balance in progress. And now we have starting of our experiment. And as you can see, the first linear portion of the curve started to emerging, and to the left we have the force increasing, and to the horizontal axis is the tensile strain. You may also hear that on the sample side there is oxide scale, or the remaining of this oxide scale is flaking off. And the straight portion of the curve is increasing, and it means that along this line, at any time we unload the sample, it will go back to its original shape without any permanent deformation. And here we see the Hooke's law in progress. So the slope that we talked about, the strain horizontally and stress vertically, gives the slope that we can use to calculate the modulus of elasticity. So now we don't have any dislocations generated. There's only bonds between atoms get stretched, and it is a flexed material flexes. So the sample will be strained and loaded until the system will recognize the yield point, so yield strength. And beyond this limit, this test will be stopped for us to remove the strain gauge. So now what's going on is material is yielding, and the yielding happens up until some point that will allow us to remove the strain gauges. And now this is exactly the moment where we need to remove the extensometer. So it is strain gauge, and the test will pause while extensometer removal takes place. And after removal, we will need to continue the test. So in general, what you can see here is this first linear portion of the curve right now, starting somewhere at 0 mark for the strain. And since we have some pre-straining of the sample, of the specimen, so we see this little gap between maybe 1,000 and 1,500 pounds, and this is because of pre-straining. And then we loaded the sample up until some yield limit, and it should be calculated using tensile strain of 0.2%. So as you can see, it is in percentage right now. So we would use this point and would project it to this curvilinear portion of the tensile curve, right parallel to this initial portion. So it's going from here down to here. So somewhere around here, we would see the yield strength, engineering yield strength. So now, with this flat behavior of the material, so it indicates that yield strength or yielding has some plateau, showing that slip systems started or they got activated, some of them, and dislocations started moving, and they probably caused some maybe geometrical change because of plastic deformation. And this geometrical change is irreversible. So when we unload the sample, it will change the shape. We will see the shape change. So I would like to also note that here, between these like marks specifically, so material deformed homogeneously up until now. And now we'll tell you where this condition will change. So it means that sample is elongated and contracted in every point equally. So it means homogeneous deformation. So what is our next task that software asks us, really? I didn't accomplish it yet, so is to remove the extensometer. So maybe I would help myself with the second hand just to safely remove the strain gauge like this and put it back. So now we're okay to continue, and I'm pressing OK, and let's see what happens next. So sample testing resumed, and as you can see that we're observing some increasing force, and since we passed this yield plateau with upper and lower values, you see that material is deformed further. More and more dislocations being generated and moved around. So from this point and up here, we see some plastic deformation and old work. So this is straining of the material that causes increase of strength. Actually, at any moment we unload here, we will see the increase of this yield strength to new level, new limit. And this is associated with dislocation movement. And dislocations start to pile up, and they will, at some point, will exhaust all this strain hardening capacity that's going on right now. And this strain hardening capacity is being exhausted now more and more, and until we reach the maximum force that this material can handle. And this is still a homogeneous deformation. So sample is being elongated and contracted evenly in every point within the volume of this middle section, at least, of the sample. And again, you see how yield strength can be increased. So moving from, or yield force, in this case, we don't have stress calculated yet, but force at the yield point. Now you see how it moved from this level to up here. So the change is substantial. And this is because this material, 1040 steel that contains 0.4% carbon, is capable of increasing strength due to deformation, since the carbon content is not so high to cause the maybe to increase brittleness of material, and also at the same time it is sufficiently enough for the strain hardening of this steel. And 1040 material, as you can see, is fairly ductile, so we see that straining of this specimen goes to pretty high levels, like 60%, 70%, And we'll talk about what is this, like 70%. What? We doubled the length? Not exactly. We observe some change in the length rather than just doubling it. And it is associated with this localized volume of material in this middle portion of the specimen. So when we now see the curve being slowed down, so it means that we will see the maximum force probably possible that this material can still handle. And at that point, the homogeneous deformation will change to inhomogeneous. And what it means is that we will start seeing some necking. And the neck will soon appear somewhere in the middle, indicating the weakest location of the sample. And there, the deformation will be localized in some point. Yes, indeed, it's now being declined. And the neck will start to emerge and be more pronounced somewhere here real soon. And what it also means that the movement of dislocations is not harmless anymore. So material started to accumulate some damage, some voids and microcracks started to generating, and these dislocations are part of this process. So after piling up, they exhausted all the strain hardening capacity of the sample, and now they act actually against the sample's integrity. So probably somewhere around here you start seeing the change in shape, and this is where I see the necking. So dramatic decrease in diameter of the sample started to occur somewhere here, where my finger is. And this reduction in cross-sectional area is, you see, associated with no further increase of force. So it means that we really are incapable of increasing or improving strength anymore. We actually leading the material towards the fracture right now. And this was the breaking point. And now, as you can see that after breakage, so sample fractured, sample failed at that point, and we see that there is a huge drop in force occurred and the machine stopped. So basically, this is the end of the test, and I would maybe just like to point out some of the critical moments related to this graph. So as you can see, sample, let me maybe just really quickly go over the sample before we jump into the discussion of the curve. So I'm removing the sample, and here I can feel it is a little hot. It is kind of warm, I would say. It's not super hot. And when we put it back together, you can clearly see that the necking region has reduced diameter around here. And when you look at this sample like this, so you may see that there is a cap and cone type of geometry. So it is sharing of the sample at the surface level and more triaxial, more complicated stress condition right in the middle of the sample, more kind of brittle behavior due to triaxiality of the stress state. There is substantial plastic deformation right above the necking region, so this is the weakest point. Okay, so let's finish the discussion around this graph and move to the last step, which is measuring the geometry after breaking the sample. So again, just a summary. This is really straight region of elastic deformation. So here we see the Hooke's law in action, and we can measure the modulus of elasticity, measuring the slope of this linear portion of the curve. So here we don't have any dislocations generated, and the atomic bonds are just stretched to some limits. Maybe, and limit is over here. It's called elasticity limit, beyond which you can see some weird behavior, and this region is called yielding plateau. So you see some lower boundary and upper boundary. So it is where atomic planes start to move and slip occurs. So dislocations are generated, and they're moving across the grains and throughout the volume of material more and more, starting right over here. And at some point, dislocations will be activated in probably most of the slip systems available in the material, and they will start propagating across the grains and volume, and then they are still generated, and then they move and allow the deformation of the material. And this is where the straining of the material associated with hardening, so strain hardening. And from this point up until this maximum point, this difference is called strain hardening capacity of the material. And once we've reached this maximum point, so we've exhausted all homogeneous deformation, all capacity of the material to be deformed plastically without failure. So after this point, neck started to occur, and from here to the end, there is inhomogeneous deformation, which is associated with neck and localized stress and deformation. So here we see the dislocations. They are locked, they cannot move easy, and additional force actually just really gives birth to some cracks and coalescence of voids that leads to maybe formation of some main crack, and that will lead to failure at the end. So what is also interesting about this is that aside from the yield strength that we can calculate using this force divided over initial cross-sectional area, and as well as the ultimate tensile strength by taking this force and divide it again by the original cross-sectional area. So what is interesting aside from these two facts is that we can also calculate the whole surface area under the curve, and we'll be able to calculate toughness. So toughness is simply the measurement of material to be deformed plastically without fracture, but now you know that there are two components to it. So it is fracture initiation up until this point, so energy consumed solely for the deformation purposes, and then once crack is nucleated, so it is the energy under this curve, the surface under this curve represents the energy that is required to further the crack and actually break the sample. So this is the total energy below the graph. The surface area represents the total energy that we need to supply to material if you want to break it. So, and this is, I believe, most of what we really need from this graph for now. And also, actually, with toughness, we have some measurement of ductility represented by the amount of deformation that this sample has undergone. So I hope I didn't forget anything here. Hit all the necessary important points, at least from what we can see here. And I think we're ready to move to our last final step. So we will put the sample back this way, and we will ensure that and what we will do is we will see that, okay guys, we had some marks. Now I see it is stretched to probably 3 inches, 0.1445. Let me write it down. And the diameter change, yeah, this is not the best notebook or note. So normally I have my notepad, or so I can write my stuff properly, but today I just forgot to bring it. So now my new diameter seems to be 0.3105 inches. And so we've reduced it from almost 0.5 inches down to 0.3. So you see the plastic deformation occurred and severely reduced the diameter.